Bueno, entonces, a ver, vamos a comenzar una serie de videos en teoría de probabilidad para irnos preparando para el parcial. Listo, como les había prometido. Entonces vamos a hacer la parte de probabilidad en videos. Ya hicimos una introducción en clase, hicimos una clase introductoria, un ejemplo para distribuciones clásicas, distribuciones cuánticas. Entonces ahora vamos a ver, digamos, los rudimentos de la teoría de probabilidad de manera más general. Listo, entonces, probability theory. Okay, so let's start with some definitions. So what is a random variable? So a random variable which we have spoke about in class. So random variable x has a set of x has a set of s possible outcomes. A random variable is x has a set of s possible outcomes. Okay. So what that means is that the random variable x is defined through an experiment. So what that means is that the random variable x is defined through an experiment which or whose result is unpredictable. Let's write it down. Whose result is unpredictable. Okay. Or you cannot predict with full certainty. You could maybe do a prediction, but it will have an uncertainty associated with. So, or that you cannot predict with full certainty. Okay. Now, S, which is the set of possible outcomes of a random variable x. So it can be discrete or it can be continuous. Okay, so let's example. These are the outcomes of x. So S is equal to heads or tails for the case of a coin. Okay, throwing a coin, that's the experiment. So let's write it in yellow. Throwing a coin. This is the experiment. Okay, now let's change experiment. So for instance, if I had that my set of possible outcomes is a 1, a 2, a 3, a 4, a 5, and a 6. So clearly the experiment is just throwing a die. Okay, it's 1 minute. Okay, so throwing a dice. Very good. Here, so these are a set of outcomes of a discrete random variable, okay? Very good. So S can be continuous. So example, continuous random variable. Okay, very good. So S is just a set of continuous values for an experiment, for the outcome of an experiment. So this could be, for instance, the velocity in the x direction for a particle, the velocity in the y direction of the velocity in the z direction. Okay, then this is a continuous random variable which has a set of outcomes which are continuous. To each event, we may assign a possible. Let's define what is an event first. So then, event. What is an event? A set of possible outcomes. A set of possible outcomes. Well, so what our main interest in statistical mechanics is that we're going to use probability theory to actually um, we're going to use probability theory to actually make some predictions on macroscopic observables. So then it's important that probability theory comes here somewhere in the place. So we can just state the following: to each event, to each event is assigned uh, it, it's assigned a map P of E, where E is the event, which must satisfy the following properties, which must satisfy the following properties. Okay. Okay, so which properties that must be satisfied by this function or a map P of E? So P of E must be positive definite. That's the first property. Second property, additivity. So the probability of an even A or an even B is the probability of even A union even B. So what union? Because this is a set of possible outcomes. This is a set of possible outcomes. So the union between these two sets, so it will be the probability of either A or B, okay? And this is equal to just the probability of A plus the probability of B, okay? This can be proved easily with a Venn diagram, okay? Recall Venn diagrams. Very good. Third property, normalization. So the probability of the entire set of outcomes S, which we have already defined for certain experiments, must be equal to 1, okay? S is the entire set of outcomes, okay? Now, well, the main objective here, it will be to determine the probability of a given event, okay? So our main objective is to determine the probability P of a given event, okay? How do we do that? So, as the frequency of an outcome in a large number of trials, um, mm, so that can be perhaps a way in which we can define probability. Okay, let's do it. So objective probability. So objective probability. Of course, the statistical mechanics to use objective probability, it will be rather complicated because objective probability, it requires definitely an experimental context, which will be complicated in statistical mechanics as we are dealing with a macroscopic number of degrees of freedom. This will be experimental. Okay, so as the frequency, let me do it in a different color so we can don't get confused with the title. So here, as the frequency of the outcome in a large number of trials, the frequency in a large number of trials. So basically, this is a way in which I can calculate probability from experimental data. So then the probability of event A, let's look at a large number of trials. This is important to have a properly defined probability, okay? So then a large number of trials, that means that the number of trials perhaps can tend to infinity, okay? This is the number of outcomes favorable to A divided by the number of total trials. So this is an objective way to define probability. Now, if we always think, let's think always about statistical mechanics. So if we think about statistical mechanics, they will be rather complicated. So this is not an easy task if we think about statistical mechanics. In statistical mechanics, I am rather interested in what are the possible outcomes and what are the possible configuration outcomes, and for that I will have to count a very large number of degrees of freedom. So this is not this is not coherent to use it in statistical mechanics. So then let me do an example of objective probability, and then we can move to subjective probability, which is more or less what we use in statistical mechanics. Okay. So here I'm gonna have throw a dice. Okay, now the probability for a dice. Okay, so then to get one, let me think. So this is the number of times I get a one, and this is the number of trials in which I get a one. So let's say that in 100 trials, I get 25 times a one. Okay. Let's say that if I increase the number of trials, let's say increase it to 200, I get 60 times a one. Okay. If I did 300 times, I obtain 100 times a one. So then, and from here, what I can easily conclude is that as n tends to infinity, the probability of a one tends to 1/3. Okay. This is how I would construct a probability distribution objectively from experimental data. There is another way which is more theoretical, which is called subjective probability. It's more theoretical from theoretical perspective. So I have here subjective probability. So from the perspective of subjective probability, this is more theoretical, the theoretical side. Um, so mm, we can do some stuff here. Okay, so we can do some stuff. And what we're going to do is the following. So this is based on the uncertainty among all outcomes. Okay. Here, so the probability of a dice to get a 6, for instance, it will be 1/6. There are six possibilities. And there's only one favorable to them. So then this is more theoretical. So this is exactly what we do in statistical mechanics. Uh, mm, because of the large number of degrees of freedom. Now, how can I know? How can I know if this is right or wrong? Like a perspective of subjective probability. So that this is important. So how can we test subjective probability? So basically, you test your assumption of probability because this is an assumption. This here is an assumption of probability. So you test your assumption of probability against empirics. So you test your assumption of probability against your empirics, which means your observations. Very good. So let me see. Okay, so there are some now. These are kind of like the definitions which will which will enable us to speak about probability in the context of statistical mechanics. And now I would like to define some rather important stuff about continuous distributions. Let me see. And I would like to define the characteristic function for which we may recall the Fourier transform. And how do we generate observables uh, from from it? Okay, so let me see. Okay, let's start here. So one random variable. So probability distribution for one random variable. Okay. Now, uh, so continuous random variable. Let's define the range for a continuous random variable in a range minus infinity less than x less than plus infinity. Okay, so then um, it is important to define some terms, some terminology to work with probability distribution. So cumulative probability function. So and we will work with the cumulative probability function. So then in just a minute, let me uh, let me show something. So large P of x, we will define it as cumulative probability function. Okay, which is known as CPF. Okay, very good. This is always less than one, always. Always this is the sum of the probabilities. So it's always less than one. Okay, very good. The probability density, nonetheless, it doesn't have to be less than one. It has to integrate to one. It doesn't have to be less than one. Now, we can say this. So the limit as x, the random variable, tends to infinity of the probability of x is equal to 1. Okay, very good. So if let me make a plot and see how should it look like. So this cumulative probability distribution it will look something like this. And in the limit as x tends to infinity, so this probability distribution, it should converge to 1. Okay, very good. Now let's do this. What about the probability density? The probability density function, how it relates to this cumulative probability function. So the probability density, so it will be the derivative of the cumulative probability distribution. So let's remember that this has to add to 1. So let's check that assumption. Let's check that the probability density function, let me do this. Yeah. Is it should be equal to the derivative of the cumulative probability function. Okay. So can we do this? So let me consider, we know that the integral of this probability, then a probability density. So P of x dx, it must be equal to 1. Okay, so the integral from minus infinity to plus infinity of P of x dx, it should be equal to the integral from minus infinity to plus infinity of the derivative P of x dx. And this is P of plus infinity minus P of minus infinity. This is, of course, equal to 1. This is equal to 0. This is then equal to 1. Okay. These are the cumulative probability functions. Okay. Very good. Now, what is then the probability density? Is that something that we can actually define? So that's important. Is what is it? So probability density function. Probability so P of x, this is equal to the derivative of the cumulative probability function with respect to s to x, and this is the probability. I can write this as the probability of an outcome between x and x plus dx divided by dx. This is more or less how can we define a probability density function. So then here, what we can draw, I can draw here a probability density function. It could be something like this. It is not restricted to be equal to 1 anywhere. It's just restricted. Its integration is restricted, which is a different thing. Okay. There are very much in statistical mechanics and in general in probability theory, there are very much important things that we can actually derive from a probability distribution. Okay. And in statistical mechanics, this is particularly relevant because that's how we evaluate observables. So it's important that we are able to evaluate expectation values of a random variable. Expectation values of a random variable. So this is now getting interesting with respect to probability theory. So then, just a minute. So the expectation value of a random variable x, it can be evaluated as the integral from minus infinity to infinity of x for times the probability distribution or the density function. Typically, we call it distribution of dx. Now, in the statistical mechanics, it's particularly important to evaluate the expectation value of a function of a random variable. Okay, and this is just the integral from minus infinity to infinity of the function f of x times the probability density p of x dx. Okay, very good. So here I will show you a set of important transformations that will give us some idea of how to construct the probability of the function f. Okay, let's check. So this function f, let me do the following plot. So f of x here. So I'm interested in considering the following and to ask what is the probability. I want to ask what is the probability of the function f. See? And then I want to relate the probability of the function f to the probability density of the random variable in which f depends. That's more or less what I want to do. And then I will do a little example. So just let me do this. Let's consider that this is the function f. And in this interval, this is x. And here we have x plus dx. Okay. Here we have a value of f. And here we have a value of f plus df. Okay. So I think this plot is quite, let's say, harmful. Now, what I can actually derive is the following. I can use several points. Let me see how can I show this. Let's do this better. So the probability for the function f is just the probability to obtain an outcome between f and f plus df. Okay, very good. I can show that the probability of the function f times df, so because of the integrals, the areas, this is just equal to the probability of the function of the variable x times differential of x. Okay? Okay, very good. Now, I can say the following. The probability of the function f df, this is just the sum, I can just approximate it by the sum over I of the probability of xi dxi, okay? And as such, I can write this as a total derivative in the way that the probability of the function f is just the sum over I, probability of xi, derivative of x with respect to f evaluated at xi, okay? This is an important expression, and what I really want to do, I just really want to show you how to actually evaluate this with an example, because this is what we're going to use okay, without being too deep, actually. And of course, recall normalization. That's all. And the integral from minus infinity to plus infinity of p sub f of f differential of f, this must be equal to 1. Okay, very good. Now let's try to consider, we're going to consider some example here. So example. So for f of x equals to x squared, so x is equal to plus or minus the square root of f, okay? Very good. Now, consider p of x equals to alpha times e to the minus lambda absolute value of x, and let's plot this. So then, besides knowing f of x, we actually have to know what is the probability distribution for small x. Okay, so that's important. So the probability density for small x, it will be something like this. This is x. Okay, very good. So let's normalize p of x first of all. Now, let's start by normalizing p of x. Okay, so what I have to do is this is the integral from minus infinity to plus infinity of p of x dx. This must be equal to 1, from where the integral from minus infinity to 0 because of the absolute value. So that will be minus x times minus 1, that's x. So this is alpha e to the lambda x dx plus the integral from 0 to plus infinity. This is alpha e to the minus lambda x dx. Okay. And let me do this. So this is just equal to alpha e to the lambda x divided by lambda. Okay, plus e or alpha to the minus lambda x divided times minus lambda. What are the limits? So the limits here are between 0 and plus infinity, and the limits here are between minus infinity and 0. Okay. So in 0, this is 1. So this is alpha over lambda. Okay. And this is plus, let's see. So in plus infinity, that's 0. And minus times this is plus 1. So then this is alpha over lambda. This is 2 alpha over lambda. This must be equal to 1, from where we get the alpha is just lambda over 2. Okay, and then we have the probability density is then lambda over 2 times e to the minus lambda absolute value of x. Okay, so we have properly normalized the probability distribution. Okay, very good. Now, we have to do the following. We have how many values we have here. Because what I haven't said yet, I haven't said that is what is this I? So this P of xi, what's I? I haven't said that yet. So I are the values here. Let's check just 1 minute. Are these two values here of x? Okay. So we have that x1, it will be square root of f, and x2, it will be minus the square root of f. Very good. So let's proceed. So then the probability for function f, we said that it was what? It was the sum over I of p of xi, okay, times the derivative of x with respect to f, okay, evaluated at xi. And we have two x's here, so that it shouldn't be too complicated. So we have that x is the square root of f, x is the square root of f, from where the derivative of x with respect to f is nothing but 1 over 2 square root of f. Okay, very good. Now, what we have to do here, sorry, I mixed up the notation here. Okay, very good. So what we have to do here is to then derive at xi each of these guys that we have here. So for instance, the derivative of x1 with respect to f, this is equal to 1 over 2 square root of f, and the derivative of x2 with respect to f is minus 1 over 2 square root of f. Okay. With this, I think that we can just expand this term here. So the probability for function f, this is equal to the sum over I p of xi, derivative of x with respect to f at xi. Okay, and this is equal to, let's sum, so this is the probability of x1 times the derivative of x with respect to f at x1 plus p of x2 times the derivative of x with respect to f at x2. So then this is just p of x1 times 1 over 2 square root of f plus the probability of x2 times minus 1 over 2 square root of f. Very good. So let me see, what do we have here? Minus, as the absolute value, is the absolute value of x. Okay, so very good. So this is just lambda over 2 times e to the minus lambda times the absolute value of x. So x1 is just the square root of f. And here, what we have is we have 1 over 2 square root of f. Here, we have, oh, I forgot something here. This formula here, this derivative, is just the magnitude of the derivative. Sorry, I forgot, completely forgot about that. This is the magnitude of the derivative. Because I will get like a zero somewhere, and that's not what I should get. So then I should get a zero. So, well, that has, of course, a different explanation. But it's just when I'm going to approximate this function p of f, I do it with how steep the change between x and f is, but it doesn't matter like what is the orientation of the gradient. So it just matters like how steep is the gradient. So, but here, then if I do this, then I have plus lambda over 2e to the minus lambda, absolute value of minus the square root of f. So that this is just the square root of f. Very good. So here, this is the absolute value of that. So this is just 1 over 2 square root of f. Okay. And then finally, what we get is that this is lambda over 2 e to the minus lambda square root of f. And here I have 1 over 2 square root of f plus 1 over 2 square root of f. Okay. This is lambda halves e to the minus lambda square root of f times 1 over square root of f. Very good. So okay, it's 1 minute. Okay, so then finally, here we arrive at lambda over 2 square root of f times e to the minus lambda square root of f. So what we really have to know to derive a probability distribution probability distribution for the function f is that we have to know what is the probability density for the random variable in which it depends. So then this is the basic conclusion that I want to draw here, and I want to just write down here an expression for this. Okay, sorry. I had to attend a message, an incoming message here, but I'm back. Okay, so then now uh, so something that we really want to do for statistical mechanics is to study moments of random variables. So then moments of random variables. Okay, so the moments of random variables are important because we can relate them somehow to observables in statistical mechanics. So then here we have that the moment of order m is nothing but, well, we write it like m sub m, and this is the integral from 0 to plus infinity. Well, depends on the range of the random variable, really, but xm p of x dx. Now, there is a very, very useful trick in statistical mechanics and probability theory that comes from something called the characteristic function, which we may define down here. So, characteristic function. The characteristic function, we denote it as gamma of k. Well, k is just a variable that we will relate to the Fourier transform in just a minute. So this is the expectation value of e to the minus I kx. Very important, and this is equal to the integral from 0 to plus infinity p of x e to the minus I kx differential of x. Okay, so you can see that the characteristic function is nothing but the Fourier transform of the probability density. Therefore, the probability density can be written as the inverse Fourier transform, the inverse Fourier transform of P of x, or the Fourier transform of gamma. I mean, it's the same thing. So the inverse Fourier transform, let's leave it like this. Do not confuse with notation. So then what I have is the following. So I just have P of x is equal to the integral from 0 to plus infinity of gamma of k e to the I k x dk divided by 2 pi. So that the characteristic function is a function of something similar to a wave vector. Now, the characteristic function, why is the characteristic function important? Because the characteristic function generates a set of moments, okay? So the importance of the characteristic function is that is the moment generating function. So let's show that. Now, we will show that the characteristic function is the moment generating function. And then we're going to ask, we can ask, why is that important? Then why is that important? Statistical physics, statistical mechanics is very important because the moments are related to observables. So basically the characteristic function is a function that from the probability distribution generates all set of possible observables from the moments. So then that's the importance of the characteristic function. Okay, very good. I'll be back in a minute. Bueno, entonces lo que vamos a hacer es lo siguiente. Vamos a considerar. Sorry, I just switched languages. It keeps on happening. Sometimes English, sometimes Spanish. But I just remember that we're doing this in English. So let's go back to English. So what we're going to do now is that we're going to consider the Taylor expansion for the complex exponential whose expectation value we're obtaining here. So then this is the expectation value of the sum from m equals to 0 to plus infinity. Okay. Minus I kx to the power of m divided by m factorial. The sum from m equals to 0 to plus infinity. So this here, what we can do is say that this is minus ik to the power of m divided by m factorial. And here we just have the expectation value of x to the power of m, which is the moment, the m order moment. Okay, so then if we expand this, well, you can see that you will get contributions of the order of the 0 order then just 1 plus something times the expectation value of x plus, let's say, alpha 1 plus alpha 2, expectation value of x squared plus. So then this is the moment generating function, okay? Then, of course, if we want to do the following, let me just do something. If we want to evaluate the moment, just translated by quantity x0, what we have to do is this. Now, let's consider e to the I k x0 times the gamma of k. Okay, and here, then we write the following. We write e to the I k x0 gamma of k. This is e to the I k x0 times the expectation value of e to the minus I kx. So this is nothing but the expectation value of e to the minus I k x minus x0. Okay, and this is just the sum from m equal to 0 to plus infinity of minus ik to the power of m divided by m factorial. Okay. Times here, we have the expectation value of x minus x0 to the power of m. Okay. Okay. So this is the moment generating function, but now the random variable is displaced by a quantity x0. So this function, hence e to the I k0 gamma of k generates the moment centered around x0. Okay, quite good. Quite good, quite good. Now, in the statistical mechanics, there is though an important quantity that we want to motivate, let's say physically, which is called the cumulant generating function. So this is a very important quantity, and we will argue its importance. I don't know if in this video, but perhaps in the next video. Here, I'm just going to like briefly define this moment generating function. Sorry, cumulant generating function, and then perhaps in the next video we can just do some examples. Okay. So cumulant generating function So the cumulant generating function is the natural logarithm of gamma of k. And this is the sum from n equals to 1 to plus infinity of minus I k to the power of n divided by n factorial. Okay. And times the cumulant, the nth order cumulant of x. But this is as well equal to the logarithm, the natural logarithm of the sum from n equal to 0 to plus infinity of minus I k to the power of n divided by n factorial times the expectation value of x to the power of n. Okay. And then we can write this as natural logarithm of 1 plus the sum from n equals to 1 to plus infinity of minus I k to the power of n divided by n factorial. Okay, and this is the expectation value of x to the power of n. Okay, okay, very good. So here, what we can actually see, is that we, I mean, let me see if I can do this now, or shall we do it at another time? Yeah, we can do it another time. So what I'm going to motivate is that I'm going to motivate in our next video the relationship between the cumulants and the expectation values of order n, which is by Taylor expanding logarithm of 1 plus lambda, for instance, which is this is approximately equal to lambda minus lambda squared over 2 plus lambda cubed over 3 minus lambda 4 over 4, etc. Okay, so and then we can actually establish a relationship between the cumulant expansion and the expectation values. Okay, as a just as an introductory, let's say fact, the first order cumulant is equal to the expectation value of x. So that means that the first order cumulant is equal to the first order moment. Nonetheless, the second order cumulant, it's not, is equal to expectation value of x squared minus the expectation value of x all squared, which is just sigma squared. So that means the cumulants are really the measurables of a probability distribution. So that's why they are so important. And we will find out that they are directly related with our macroscopic observables in statistical mechanics. So this is all I had to say for today. Or for this video, I will be recording the other videos for probability later on this afternoon. So, and I will be uploading this to my channel in brief. Thank you very much for your attention.